I have a question for you, Xiao. So what if I want to spin up a database on that kind of I/O system? Is that possible, or is it?
It's been a database for a indefinitely long time, right?
Yeah, something like that.
To be honest, I don't think you can do this in tech. Like we have 48-hour wall time for most of our resources, but we can figure out. Yeah, we do have use cases. Yeah.
Thanks everyone. That was a real treat. In the federated and cooperated, I can't say the word, learning.
Competitive.
Yeah, competitive. Sorry, I'll get it.
Oh, that's great. Yeah.
You didn't talk much about incentives for these parties to actually give good data so that other competitors could actually get good models out of that, including themselves. Is there, have you thought about threat models where somebody who's pretending to cooperate is actually sending corrupted data intentionally to kind of screw up the models? That's kind of one question. And then relatedly, you sort of seem to talk about it mostly as a software solution, but since we have the Intel person here, can we also talk a little about encrypted enclaves and what you see as the future for your work with encrypted hardware and where Intel's going with that?
Yeah, great question. So regarding the first question, I didn't really mention it when I talk about Helen, because for that particular piece of work, the incentives was a little bit complementary to the work that we did. But actually, in a follow-up work, the MC squared one, which I briefly flashed, I guess, on the slides, we're really trying to. We're also thinking about the incentives problem. So what we actually allow you to do is to, in that paper, we define the idea of release policies. So what you can do is, for example, there are some machine learning techniques where for you to actually check how much training data is embedded in the model. So that check, you can actually express that in MPC as a release policy, so that if you're not happy with the model at the end, you don't actually have to reveal the model, right, to any party. There are some economics incentives that you might want to, you can also encode in MPC, whereas, for example, I've talked about the banks competing with each other, right? So you could imagine a bank might want to have a policy where it wants to make sure that the economic gains that it gets from doing this collaborative training actually is maybe high enough and isn't like super outmatched by the economic gains by its competitor, right? So that you can actually formulate that as a validation phase or testing phase at the end. And again, you can choose not to release the model at the end if you're not happy with the economic gains you're getting. In terms of the hardware enclave, so actually before I started working on MPC on the more crypto side of things, I worked on a project called Opaque, which is a secure SQL system on top of Spark SQL that uses Intel SGX hardware enclaves. And I would say that there are some trade-offs, of course, that between hardware enclaves and cryptography. For example, hardware enclaves, because you have this trust hardware, right? It's just going to be a lot faster than if you had to express everything using heavyweight crypto. But at the same time, it is prone to side channel leakage. So for example, you can actually learn things from just a memory access pattern of the program that you're running, learn about the secret data that you put inside the enclave. And I think that really it depends on the application, the type of data you're protecting, right? Security isn't black and white. It has many, it's very grayish, right? It has many levels of security. That's why you should always think about the application that you're running, the data that you're protecting, the economics, right? How much value does your data have? And think about the threat model that corresponds to the application and choose the best solution for that.
So in my own group, privacy is the biggest thing we're working on. About half the team is working on privacy. So in addition to multi-party computation, we're doing homomorphic encryption and differential privacy, and we're also thinking about kinds of hardware to build for the integer operations and polynomial operations that you have to do for things like homomorphic encryption. SGX is getting additional features, but as you mentioned, one of the flaws is the side channel attacks, which if I talk about, I'll be shot by somebody, I think. But it's one of the biggest things that we get asked by our customers is how do we share data, how do we monetize data, how do we keep it private?
So this might be a little outside the comfort zone, but if, as Intel, what is, from a materials side, if you could design one like ideal material, what are you looking for in terms of your device performance? Are you looking for increased coupled functionalities in your materials, like that multi-ferroic system, or something simple like high K dielectrics that work at high speeds really important? Like, what's the most important?
So, I mean, I would like to know what you guys think, including Eric. The thing that we want is a better transistor. We want to use boring Boolean logic, be able to manufacture it at scale. Just we want lower voltages, some indication that you're going to have generations of scaling, and we want memory, interconnect, and compute, all those three things. That's why this Meso device is very attractive. So I think the answer is we want a Boolean logic. We don't want neuromorphic. We don't want stochastic, because we don't know what to do with it. Maybe we have to do deep learning. Our customers use deep learning. If you go to them with a Monte Carlo sampler, they're not going to be super happy.
I mean, they'll be happy in expectation.
That's right.
Well, I mean, that's a joke. Something I didn't appreciate was just the degree to which there's like literally $1 trillion of kind of CapEx and R&D invested in our current silicon trajectory, and I always told my co-founders at Navia, the first startup that we did, which to be clear went out of business because hardware is hard, that you're never going to win betting against Intel. And I still kind of feel like that's the case, where for almost all of our kind of existing computing infrastructure needs, you guys are basically where it's at. And I would make the argument that the blip that we see right now with Nvidia is actually kind of an artifact. And in spite of what you might have seen with Nvidia's stock run up, I think that in 5 to 8 years we'll be like Nvidia who, because the existing companies with what I think of as kind of the superior run on the semiconductor technology will be in them. But I don't know. I do not trade on this information.
We love your work. I mean, the material you're making of the ferroelectric material, that's really I think that is the most worthwhile thing to work on. That is the future of our field. Is new material science material.
Hi, thanks for all your talks. I also have an Intel-related question for Amir. I'm not sure if you can answer this one or not, but so last semester I was playing around with the Google Vision Kit, which is basically this cardboard with a Raspberry Pi inside as a camera and the Intel Movitus Murad VPU chip. So it has a camera, right? So it does all this nice, like it reduces your face. You can tell if you're smiling or not, and will like turn yellow and blink and stuff, and it's really fun. And so I wanted to do face recognition on it. And right now the chip is only supports TensorFlow and Caffe frameworks, and like a lot of the neural nets that are more for face recognition have a DLib framework.
A what framework?
DLib. And
never heard of it.
Yeah, so it's Adam Gitke. He has like all these cool neural nets, and kind of the one that everybody's using for face recognition is this one. So I was wondering sort of how the decisions are made for which frameworks are this chip support.
Good question. It's a really difficult and laborious process. The main customers for Intel are Google, Facebook, Microsoft, AWS. They're all at each other's throats, and they all have their own frameworks and all their own software, and they want people to adopt it. So they come to us and say, you better do TensorFlow. The other one says, you better do Torch. So we're basically negotiating all these things, and I have to add DLib to your list. And now you're an angry customer. So we'll get on it.
I can add a little bit to that question. It's like one indicator is to look at like this open source repository, how much Intel contributes. Like Intel contributes a lot to Caffe, to TensorFlow optimizations, but probably not MXNet. So that's the indicator. Yeah, the hardware will support Caffe and TensorFlow.
Yeah, so one of the challenges with Intel is that we try to make software and then nobody uses it. So we don't know if we should support TensorFlow and let Google dominate the world, or we should build software for all of us that's open source. Just no one will use it. So it's really, really challenging for Intel to do anything other than semiconductor manufacturing. I constantly get asked, can you figure out other business models to help Intel get out of semiconductors? And it's work in progress. Working with you guys informs us on other things we can do. So privacy is one of them, actually.
This is a question from someone, from a physicist who mostly thinks about exploding stars to the machine learners. So like when I played around with the emulator, in the end, like, you know, I put it on my MacBook Pro and like, you know, fit the neural network over, I don't know, 6 hours or something like this, and then got something reasonable out. But you guys are making these hardware things like faster and faster. So I'm wondering, like, in general, as I don't have a feeling for this, is this because like people train very complex networks, or do they train many because they do hyperparameter optimization? Or what is the need for, like, you know, these really fast TPUs and GPUs? Just out of interest, because I mean, for my application, it wasn't necessary. But I'm wondering, like, you know, what are the applications that you sort of need?
Can I just ask, and I think this is really a question for the supercomputer and Intel person, but can I ask, like, what did you do during that 6 hours while it was training?
Oh, I was going outside. It was Memorial Day. I had a beer and things like this. So.
I see. Okay, just making sure. I mean, my joke is always that the deep learning grad students are always really fit because they get to go to the gym a lot because they don't have a lot of else to do.
No, I didn't do that.
But on our side, we're always, you know, if it takes 6 to 12 hours to try and train a new model, that really does kind of inhibit your ability to do kind of innovation, right? Even if you try a bunch of parameters kind of simultaneously. Well, I don't want to call it, so I don't want to call it hyperparameter optimization because it's not just about hyperparameters. It's about kind of, it's not about scalars necessarily that you're adjusting with your model. There's a modeling process, right? Just like with any other sort of statistical modeling, just like when I was doing MCMC, if it takes, you know, 6 or 12 hours for my MCMC chain to mix, like that's a bottleneck on a class of experiment that I've done. And I think for at least a lot of the sorts of problems that I've worked on, that's a real impediment. But
Yeah, it's sometimes about productivity, right? So assuming you're training a transient detection model, I mean, using like a month of LSSD data, right? I mean, if you're just using one GPU, that might take you a year. And running it at a larger scale and running it faster can definitely train a model with a satisfying robustness, and you can put it into production in time to do timely detection, right? So that's why we're trying to run it fast, but without losing test performance.
I don't have any.
Zhao, can I ask you a question on that then? So I'll exploit my opportunity as a panelist. For the sorts of results you guys show where you like train ImageNet in like -37 seconds or something, do you, like, how much does that work to other models, and how much effort is that to kind of get your model or get your code in a position where you can see those kind of parallelism speed ups? Like, is that because like I know you're kind of classically a systems person too, and like very, very good at like computers, right? And for those of us who are more on the theory side and are perhaps less good, like, is that ever approachable to us? Is that something where we need like 2 or 3 software engineers for, or do orgs like TAC have kind of infrastructure for us to parallelize our models kind of quickly and easily that way?
I got what you say. Can you say a little bit more clear about your question? Like.
Yeah. So if I give you a model that currently takes 3 weeks to train, how much effort will it take to get it to the point where it can train on 1,000 GPUs in like 37 minutes?
Okay. So that requires hyperparameter tuning that takes quite a long time for us to make this work. Like 2 weeks, I would say. Like for this case, 2 or 3 weeks.
Of engineering to kind of get it to the point where then you can kind of go.
And still need to wait for. Your job needs to wait in the queue to get that many resources, right?
Sorry, again, it's not really a question, but more of a comment, which is that I think it's interesting that we came full circle, because yesterday we were talking about engineering our optics, designing our optics and engineering our optic design, thinking about the analysis, and so building them together with the analysis. And we're actually getting to the point where our computer is built together with the machine learning that we will do on it. And, you know, in a way, it's great for optimizing, and in a way, it's really, really scary because transferability becomes a problem.
So, okay, I'm going to use, and then you'll have the last. So, I've been thinking about this design of what I would call boutique computing, if you will. Basically because I've been at Berkeley Lab for 20-some odd years. I've watched all the machines they've brought in, and basically I think they've reached their peak. We're not going to have computing performance, I think, based upon the standard designs that are there, throwing GPUs on them. We just hit what we can do with a large-scale machine. So I really like the idea of tackling specific problems with new architectures and making that run faster. And I just wanted to get an idea of how efficient do you think this can be? What is the win from designing something on an FPGA to burning an ASICs and then, you know, making the world's best 3D FFT machine for some LAMPS material science code, or designing, you know, what's the return on investment? Because right now the DOE is looking at building $100 million machines, and they're going to likely run at 1% efficiency. And so if I could do a machine for $10 million that had 50% efficiency, I'd win. So you just wanted your, and also I really like to talk on the file I/O, which is where I think the next big problem is coming, is we're going to move to non-POSIX file systems at some point, and handling that I think is an issue too. So I just wanted some of your thoughts on that.
So I love this question because when I was defending my PhD thesis, a friend of mine, Dan Roy, who's now a theoretical stats professor at University of Toronto, said, "Eric, why are you doing all of this? You're just getting a constant factor speed up." And I said, well, that's true, but you know, my life is measured in constant factors. I honestly think that we're looking at, I think that if you do if you go all the way to a custom ASIC with kind of the conventional algorithms that we're talking about, you get maybe a factor of 10 to 20, right? If you're good, which is not zero. But if we see if these process node improvements really are tapering out, then that's kind of, it makes me worry about the future for my non-existent children.
Well, my point of view is really like we are driven by users, right? So it really depends on what users' workload look like. But if you think about our cell phones, like they have different DSPs for, I don't know, for sound, for video. There are a lot of chips in there, right, for different type of tasks. So that's definitely one way to go. But again, depending on the users, and users are you guys, right? So depending on the applications.
I don't have very much I share your concerns, and I've been pushing really hard on the new material side. And these materials have been around for, you know very well, they've been around for a long time. So there's a lot of skepticism. What's different now? It's we really need it. We have all this data, and our compute is just slowed down dramatically. And I've worked on nurse machines as a student, and yeah, I think we shouldn't be building any more supercomputers. We should be investing all that money and coming up with new materials. So I'm not sure how much microarchitectures are going to get you. David Patterson, who is a professor at Berkeley, says this is an era of new microarchitectures. I think that's also mostly played out, and I would like to hear opinions about that. But we have the physics, we have the materials, we have someone here who is building really cool things. It's very difficult to manufacture, scale, and do certain kind of computations with them, but we can figure it out. It's a grand challenge, and as a company, Intel is underinvested in this area, and this is Intel's bread and butter. Thin film oxides and chemistry, and so it's surprising.
Question: do you need a supercomputer to design new material?
If you have one, give it to me. No, we don't.
All right, last question here.
So I had a question for Wenting. So I think your talk was really interesting to me, and I think it has a lot of applications in astrophysics, especially in multi-messenger subterrestrial searches, because observatories are very reluctant to share their subterrestrial data with a central hub, something like SEMA project or Astrophysical Multi-Messenger Observatory Network or any other framework. So I was wondering, like in general,
if you or any of your colleagues have thought about astrophysics or privacy of the data in astrophysics.
We have been, as I mentioned, the use cases that I actually talked about are real use cases. So we've been collaborating with with banks and financial use case. And like I mentioned earlier, I just had a meeting with earlier today with a nuclear engineering student on nuclear auditing, how to do that securely and without, by keeping the nuclear facilities data private. And we actually, I talked yesterday to a cardiologist from UCSF about how to actually train medical models from different institutions securely. So yeah, I think, again, so our approach, or one of our main approaches, is to really co-design machine learning, security, or crypto, I guess, along with system together. So for us, it will be really useful to know about the specific algorithm that you want to run. That would give us an idea of how to make that more efficient. Yeah.
Can I make a quick comment? Do you have an answer along those lines of
Want to ask a really, really quick question?
Yeah, very provocative. So why are you so attached to digital technology? What about analog computers? Yeah, in the 60s they were great.
Well, so there's lots of different substrates, right? Not just digital analog as we kind of traditionally invite. One of the challenges with a lot of analog computing infrastructure is that noise enters in this kind of destructively linear way. But also there's just this issue of scale, right? Building large analog circuits is incredibly difficult, right? The lack of kind of digital design discipline means that a lot of the fabrication challenges that we see on digital are just worse than analog. And I think that's one of the things. I mean, everyone would love to come up with good, exciting new kind of computing substrates that we could scale up to kind of the million or billion node scale. But analog's hard. People are interested in this. Quantum is like a different version of that, right? But it's hard.
All right, let's thank all the speakers again. And last but not least is Patrick, who is going to wrap this all up in a nice bow.